Okay, the final method we are going to see of solving recurrence relation is the master theorem method. Okay, so this is like a cookbook approach for solving recurrence relation. So the method is applicable for this kind of relations where Tn is in the form A Tn over B plus Fn, where A is greater or equal to 1 and B is greater than 1, strictly greater than 1, because we have to divide the input size at least by 2. Okay, the input size shouldn't remain fixed. And Fn is asymptotically positive, as we've been emphasizing. The Fn, we want it to be in this quadrant. It has to be a positive function. N divided by b may not be an integer, it may be a fraction, but usually we will consider the floor or the ceiling, because normally we will convert it to an integer. Of course, the theorem requires memorization of the 3 cases. So if you're going to use it in an exam, for example, to solve a recurrence, you have to be able to remember the formulation. Alright, so let's begin by first of all stating the theorem. So the master theorem states that let A be greater or equal to 1 and B be strictly greater than 1, B constants. So A and B are constants. Let Fn be a function, and let Tn be defined on non-negative integers by the recurrence of the form Tn equal to A Tn over B plus Fn, where, as I said, we can replace N over B by the floor or the ceiling of N over B. If all these conditions are satisfied, then Tn can be bounded asymptotically in 3 cases. Case number 1. If Fn is big O of n to power log of A to base B minus some positive number epsilon, then the running time Tn is simply going to be theta of n to power log of A to base B. Case 2. If Fn is equal to theta of n to power log of A to base B, then Tn is theta of n to power log of A to base B all times Lg of n. Remember, Lg stands for log to base 2 of n. And the final case, if Fn is big omega of n to power log of A to base B plus some epsilon for some epsilon greater than 0, and so here you have to be careful, there are 2 conditions. Okay, if this is true and A times f of n over b is less than or equal to some constant c times fn, where c is less than 1. So this is basically trying to ensure that fn is monotonically increasing. We will see this when we come to the example. So if we have these 2 conditions, then we can say that Tn is theta of Fn. So this is a theorem. Sounds a little complicated, but actually it's much simpler than it sounds. Let's try to simplify it a little bit further. Okay, I stated the 3 cases once again, and let us try to see what they actually mean. So intuitively, what we are saying is it is the larger of the 2 functions. If you notice, we have 2 functions that we are comparing in each of the cases, either Fn or n to power log of A to base B. So it is the larger of the 2 functions, that will determine the running time. The larger of either fn or n to power log of a to base b. So in case 1, we are saying if fn is bigger of n to power log of a to base b minus some positive constant epsilon. What we are really saying here, remember the definition of big O, it means fn is less than or equal to big O of n to power log of a to base b minus some epsilon. So in that case, it means fn is the smaller. This is the bigger. So it will determine the value of the running time. So that's why we are saying here, for example, Tn then will be theta of n to power log of a to base b. Here in case 2, they are actually equal, because remember theta means equal. So if they are equal, take any of them, either the fn or the n to power log of a to base b, they are equal anyway, and multiply the result by log to base 2 of n, and that is the answer. So Tn will be theta of n log of a to base b, or fn, because they are actually equal, times log of n to base 2. On the other hand, if it is the fn that is greater, because remember big omega means fn is greater or equal to, okay, fn is greater or equal to the gn, some constant multiple of the gn, which is in this case n to power log of a to base b. So if fn is the greater one, then it is going to be the result, and the running time Tn is going to be theta of the fn. The only thing to remember is there are 2 conditions to check here, not only that fn is this, but also this function, this inequality is also true for some c less than 1. So we will see this, we will see many examples to show how this works, but basically this is what we are saying, that in case 3 it is the fn that is larger, and therefore Tn is theta of fn, whereas in case 2 the 2 functions have the same size. In other words, they run at the same rate, so we simply multiply one of them by logarithmic factor, and we will have Tn equal to theta of n to power log of a to base b times Lg of n, or theta of fn times Lg of n, either way. Alright, so I hope this gives you more sense of what the theorem is trying to say, but we will better understand when we take examples. So we're going to take several examples trying to demonstrate this idea. Let us start with this one. Tn is equal to 16 Tn over 4 plus n. Clearly it is in the form that we can apply the master theorem, where, so I keep repeating the theorem in each of the examples, but you have to remember to memorize it, because in an exam or quiz nobody will give you the theorem, you have to remember it yourself. So, but this is how to proceed. We need to find these values based on the recurrence that we have. What is the value of a, what is the value of b, what is fn, and what is n to power log of a to base b. If we can find all of this, then we just need to look and see which of the 3 cases it is, and that will determine what will be the running time. So clearly a is equal to 16, b is equal to 4, and our fn is just n. So fn is equal to n. So the next question is, what is n to power log of a to base b? So n to power log of a to base b is basically going to be n to power log of 16 to base 4. N to power log of 16. Remember, A, we just said is 16, and B is 4. So the question is, what is n to power log of 16 to base 4? Well, 16 is the same as 4 square. So we can say this is n to power log of 4 square to base 4. Alright, and this is clearly 2, so n to power 2 log of 4 to base 4. And this is 1. So we can clearly say this is n square. Okay, this is what we have just said here. This is equal to n square. So we have found n to power log of a to base b. The question is, which is bigger? Is this bigger or fn is bigger? Those are the two functions we will be comparing. So clearly the n square, of course, is bigger, because even if we subtract something very small from the power of n here, for example, let's say we subtract half, let's say epsilon is half, then we will still have n to power 1.5. Well, n, which is our fn, will still be less than or equal to that, even if we subtract some positive constant. So that's the idea. Once you find your n to power log of a to base b, you will ask, which of these three cases does it match? Yani, is n equal to big O of your result minus some small number epsilon? Or is it theta of n square? Or is it big omega of 2 plus some constant epsilon? Okay, clearly it is the first case here that matches. N will be big O of n square minus some small positive constant. Okay, so we can say therefore our running time Tn is simply theta of n square. This n to power log of a to base b is n square. So we can make that conclusion. We say it is case 1, and the answer is theta of n square. In other words, Tn is theta of n square. So this is basically how to apply the algorithm. You have to find the values of a, b, and fn, compute n to power log of a to base b, and then do the comparison, decide which case it is, and automatically you know the answer. Let's take another example. Tn equal to Tn over 2 plus 2 to power n. Okay, this is exponential function. So most likely it's going to be case 3. The fn is likely to be bigger, but we will check and see. Type. So A is 1 in this case. There is only one sub-problem. But the size of the input is divided into 2, so B is equal to 2. And Fn is 2 to power n. So next we have to compute n to power log of a to base b. So this is obviously n to power log of 1 to base 2. Okay, we know that log of 1 is always 0. So this is actually n to power 0, which is constant. Okay, so the question is, which is bigger, this constant value or 2 to power n? Definitely 2 to power n is going to be bigger. Okay, yeah, so if you add something little to the 0 that we have here, 2 to power n is still going to be greater or equal to that n to power small number epsilon. So it is actually the case 3. But remember, case 3, we have two things to check actually. Not only do we have to do this comparison, but we also have to find a c which is less than 1 that satisfies this inequality. So we have to have the two cases before we can make the conclusion. So Is it case 3? Yes, if you can also satisfy the second condition. So let's see what the second condition says. Okay, so here A is 1, remember, so nothing here. But what is Fn over B? If you replace n here with n over b, well, b is 2. So basically you have your Fn over b will simply be 2 to power n over 2. So this is what we have on the left side of this inequality. We are supposed to find some constant c less than 1 for which the result is also less than or equal to Fn. Well, Fn is 2 to power n. Okay, so the question is, can we find a c that is less than 1? And remember, c also has to be positive, so it's basically saying between 0 and 1. Okay, for which this inequality is true. Now here you can take actually any constant that you can find within this range that will help you to satisfy it. It's not a fixed value. So we are saying, suppose for example you take c to be half. Suppose you take c to be half. Put it back in that inequality and see, is it going to hold? Okay, so the left hand side remains of course as before, but now we are replacing c with half times your Fn, which is 2 to power n. Now clearly half is 2 to power minus 1. So now we have 2 to power minus 1 times 2 to power n. Clearly that is 2 to power n minus 1. The question is 2 to power n over 2 less than or equal to 2 to power n minus 1? Definitely yes. See, here we are only subtracting 1 from n, but here we are dividing n by 2. So definitely the left side is much smaller than the right hand side. So the extra condition in case 3 is also satisfied, and therefore we can conclude Tn is theta of 2 to power n. Example number 3, Tn is equal to 2t of n over 2 plus n. So again you have to find your values a, b, and fn. So obviously a is equal to 2, also b is equal to 2, and fn in this case is n. So if you compute n to power log of a to base b, it's going to be n to power log of 2 to base 2. And log of 2 to base 2 is definitely 1. So actually you have n. So now this is interesting. As you can see, they are equal. Fn is n, log of n, n to power log of a to base b is also n. So clearly case 2 applies. They are equal. Fn is theta of n to power log of a to base b. Therefore, if you try to answer which of these 3 cases it is clearly the middle one here, the second case. So case 2 applies, and you can say your Tn is theta of n. Okay, we evaluated this to be n log n. Okay, so theta of n log n. Now if you think of this carefully, this is not a new running time for us. This is actually the running time of merge sort. If you remember, merge sort was 2 times Tn over 2 plus the running time of the merge, which was n. We proved it last time that it was n log n. But now using master theorem, we can also see it is the same thing, theta of n log n. Okay, another example, Tn equal to 16 Tn over 4 plus n factorial. So definitely this is going to be another big Fn. N factorial is a very big function. So but let's see. A is 16, B is 4, Fn is n factorial. So what is n to power log of a to base b? Is going to be n to power log of 16 to base 4, and 16 is 4 square, so this is actually just n square. So now the question, which of the three cases is it? Can we say n factorial is bigger of n square minus some small value? Or is it going to be theta of n square? Or is it going to be omega of n square plus some epsilon? It is definitely the latter one. This is case 3. And the n factorial, if you remember, is n times n minus 1 times n minus 2. So it's almost like saying n to power n. Okay, so it is definitely bigger than just n square plus some positive constant epsilon. So it seems to be case 3, but only if we can also prove the other half of the condition. Can we find a constant c less than 1 for which this inequality is true? Is 16 times n over 4 factorial, because that's the meaning of a fn over b. A is 16, as you can see. Fn over b, where b is 4, is like saying n over 4 factorial. Remember, Fn means n factorial. So if n is n over b, which in this case is 4, so we're going to have n over 4 factorial. So the question is, can we find a constant c such that that is less than c times the n factorial itself, which is the Fn? Okay, let's try and see. So let's again take c to be half and see what we will have. So if you take c to be half, then c n factorial will be equal to half n factorial. And clearly, half n factorial is greater than n over 2 factorial, because this we are finding the complete n factorial and then just dividing it by 2. But here we will find the factorial of n over 2, so it's going to be much smaller number. So based on this, if we now substitute back to our inequality here, we will be able to say this 16n over 4 factorial is definitely less than or equal to n over 2 factorial. Yani, instead of finding n over 4 factorial, we find n over 2 factorial. N over 2 factorial is much bigger. Okay, and that itself is less than or equal to half n factorial. So clearly this is less than half n factorial. So if we take our c to be half, that inequality is also true. So we can conclusively say our running time function is theta of n factorial. Yet another example, Tn equal to square root of 2 Tn over 2 log n. Alright. Okay, reminding you the theorem again for easy reference. But to proceed, we have to find the value of a, b, and fn. Well, a is root 2, b is 2, and fn is log n. So what is 2 to the power log of a to base b? It's going to be n to the power log of root 2 to base 2. But we all know root 2 means 2 to the power half. So you can actually bring the half here, and you will have log of 2 to base 2, which is 1. So you will be ending up with n to the power half. So this is n to power half, which is square root of n. So the question is, which is bigger, the square root of n or log n? Definitely square root of n is bigger than log n. Log is a very small function, very slow growing function. Just take, for example, 100 and take the log to base 10. Log of 100 to base 10 is 2, but square root of 100 is 10. So the square root function is really much bigger. Alright, so this time it is n to power log of a to base b that is bigger, and therefore it is going to be our running time. Theta of that will be our running time. So the conclusion is it is case 1, and the running time is going to be theta of square root of n, which is equivalent to our n to power log of a to base b. Okay, I think the last example, Tn equal to 4, Tn over 2 plus n. So A is 4, B is 2, and Fn is n. So n to power log of A to base B is going to be n to power log of 4 to base 2, which is n square. So clearly n square is again bigger than n. So again we're going to have theta of n square. Alright, so that's the end of the examples. These are exercises for you to try. Tn equal to 2 Tn over 3, Tn equal to 7 Tn over 7 plus n, Tn equal to 8 Tn over 2 plus n cubed. These are directly from the book actually. First one says show that Tn, which is equal to Tn minus 1 plus n, is big O of n square. And 2, use a recursive tree to determine a good asymptotic upper bound on the recurrence Tn equal to Tn over 2 plus n square. After that, use substitution method to verify your answer. So use the master theorem to give a tight asymptotic bound for each of the following: Tn equal to 2 Tn over 4 plus 1, Tn equal to 2 Tn over 4 plus root n, Tn equal to 2 Tn over 4 plus n, and finally Tn equal to 2 Tn over 4 plus n square. Okay, the last exercise, it says use the master theorem method to show that the solution to the binary search recurrence is indeed log n, as we said. Okay, so this is the recurrence Tn equal to Tn over 2 plus some constant action theta of 1. Show that it is theta of log n. You can replace this theta of 1 with a constant c, for example. Right, so that's the end of the exercises and the end of the lecture. I hope by this you will have learned now how to solve recurrence relation using the 3 method of master theorem, a recursive tree, and the substitution method. Thank you very much.